Hello and welcome to Week 10, Lecture 2 for Math A37. So in the last few lectures, we've been talking about sequences, convergence of sequences, tests to see if sequences converge, and so on. Today we'll be talking about series, which are very closely related to sequences. Before I start talking about the formal definition, let me just give a classic example to motivate why we study series. Suppose we have a turtle. So this here is my impression of a turtle. And suppose a turtle moves from say x equals 0 to x equals 1. So the turtle goes from 0 to 1. That means that the distance traveled by the turtle is equal to 1. Distance traveled. But also, for the turtle to go from 0 to 1, it must first go from 0 to 1/2. So it must first travel this distance here. So this is 1/2. Plus, it must go now from 1/2 to 1/4. So 1/4. So it must travel this distance, so plus 1/4. And then it must go to 1/8. And so on and so forth. So this is plus 1/8. Then must go half of that, which is 1/16, plus 1/32, and so on, all the way up to infinity. Up until now, we've only really talked about adding up a finite number of numbers. But in this case, we can see that this infinite sum of numbers actually, for this problem to make sense, must equal 1. This leads us to believe that there's a way to add up an infinite number of infinite sequence of numbers and have it add up to a finite value. And this is what the study of series is all about. So I'll begin with a formal definition. Definition: a series which we'll denote using sigma notation from k equals 1 all the way to infinity of ak is the sum of the terms of the sequence ak. Of the sequence ak. Right, so that means that the sum from k equals 1 to infinity of ak is equal to a1 plus a2 plus a3 plus and so on, all the way up to infinity. Notice that we're using the same sigma notation that we talked about at the beginning of this course, with the only difference being that instead of having an ending value of m, we have the ending value infinity. Also, we refer to ak as the kth term in the series. So some examples of series include the series of the sum 1 over k from k equals 1 to infinity. So this would be 1 plus 1/2 plus 1/3 all the way up to infinity. Also, we may have the sum of just k, which is equal to 1 plus 2 plus 3 plus 4, again all the way up to infinity, or something along the lines of infinity of 1 over k squared. So this goes 1 plus 1/4 plus 1/9 plus 1/16 plus and so on. Right now we haven't defined what it means for these to equal to something. For now, series is just a formal sum of infinite sequence of numbers. To define what it means for a series to equal to a finite value, we first need to define the partial sum. So given a series AK, the sum of AK from k equals 1 to infinity, we define the nth partial sum, which we'll denote as Sn, as the sum of the first entries, or n terms in the series. So k equals 1 all the way up to n, plus all the way up to an. The collection of Sn form a sequence, and we call this sequence Sn, and we call it the sequence of partial sums. Sequence of partial sums. So if I look at the partial sums, starting with S1, we see that S1 is just equal to A1, and S2 is equal to A1 plus A2. S3 is equal to A1 plus A2 plus A3, and so on, where Sk is equal to A1 plus A2 plus Ak. From this, we observe that the whole series, which is the sum of all the Ak's up to infinity, is equal to the limit as n goes to infinity of Sn. So this allows us to define what it means for a series to be convergent or to add up to a finite value. So definition. We say a series converges to if the sequence of partial sums which we denoted as Sn, converges to L. So in other words, the sum from k equals 1 to infinity of Ak is equal to L if the limit as k goes to infinity of Sk, or I should use Sn here, limit as n goes to infinity of Sn is equal to L. And the limit as n goes to infinity of Sn is just the limit of a sequence. We've formally defined what it means for a sequence to converge to a value L in the last few lectures. So we use that definition here to define what it means for a series to converge to a value L. Or in other words, what it means for an infinite sequence of numbers to add up to L. And of course, we say that the series diverges if the sequence of partial sums Sn diverges. And again, we know what it means for a sequence to diverge. So we use that to define what it means for a series to diverge. So let's see a few examples of how we can use the definition to show if a series converges or diverges. So the first example is the series, the sum of k equals 1 to infinity of just k. So this is just 1 plus 2 plus 3 plus 4, so on. In this case, the partial sum, Sn, is equal to the sum of 1 plus 2 all the way up to n, which, if you recall from the first assignment, or rather A0, is equal to n times n plus 1 over 2. Now in this case, the sequence Sn is not bounded, because as we make n larger and larger, the numerator gets larger and larger, and Sn goes to infinity. And what we learned in the last lecture was that if you have a sequence that's unbounded, it diverges. So therefore, Sn is not bounded. Therefore, Sn diverges. So by the definition of a divergent series, the series also diverges. And this should come as no surprise, because if we add up all the natural numbers, we will obviously get infinity, and therefore it diverges. It does not have a finite value. Okay, let's look at another example. So let's look at the series from k equals 2 this time to infinity of 1 over k squared minus 1. Notice that we're starting at k equals 2 here. The starting point doesn't matter. What matters is that the sum is going off to infinity. So in this case, Sn will be equal to, well, we start at a2, so S1 is not defined, but the limit of the sequence definition does not change. So it goes from a2 all the way up to an for n greater than or equal to 2. And the general formula for Sn in this example is actually equal to 3/4 minus 1 over 2n minus 1 over 2 times n plus 1. This can be shown by using induction on n. I'll again leave that as an exercise for you guys if you want to try it at home. But from here we can see that Sn converges. So the limit as n goes to infinity of Sn is equal to, recall from the properties of convergence of sequences, we can split the limit amongst the different terms. So this is equal to limit as n goes to infinity of 3/4 minus limit as n goes to infinity of 1 over 2n minus limit as n goes to infinity of 1 over 2n plus 1. And both these limits go, this limit goes to 0 and this limit goes to 0, and this is of course equal to just 3/4. So therefore, this limit is equal to 3/4, which means that the series converges and equals 3/4. Now this definition of convergence of series is very intuitive and makes a lot of sense, but in practice it's not very useful because for a lot of series it's hard to come up with a closed solution, a closed form for the partial sums like we have in this example. This was actually one of the only examples I could find where there was a closed form for Sn. So in general, we're going to develop a lot of techniques to determine if series converge or diverge in the coming later today and in the next few lectures. But before we do that, let's look at some properties of series. So we'll start with a theorem on sums and constant multiples of series. Constant multiples of series. So theorem, suppose we have two different convergent series. BK are convergent series. Then the following is true. A, the series of CAK is equal to C times the original series. Okay. And B, the sum of the two series, AK plus the series bk is equal to the series of the sums of this of each term. So ak plus bk from k equals 1 to infinity. Now these two statements may seem obvious because they are true if we are adding up a finite number of numbers, but in this case, since we've defined what it means for the sum of an infinite amount of numbers to add up to something, we need to check that these properties are consistent with that definition. So we will start by doing a proof. So proof for A. Proof of A. So we're looking at the series CAK, k equals 1 to infinity, and we know by definition that this is equal to the limit as n goes to infinity of the partial sum. And the partial sum here I'll write as in segmentization, so it's from k equals 1 to n of CAK. And this is the definition of series convergence. Series convergence. Well, in this case, we can bring the constant c outside of the sum. So this is c times k, the sum. Okay, oops, sorry, this should be up to n by property of sums. And we know that limits commute with constant multiples. So this is equal to c times the limit as n goes to infinity of ak by property of limits. And finally, note that this sum is simply the partial sum for the series AK. So this is equal to c times the series k equals 1 to infinity of AK. So this here is the limit of partial sums, and this is the definition of series convergence. And note the series we assumed, the series AK does converge to a finite value. And the proof for B is very similar to this. So again, we start with the series AK plus BK. By definition of series convergence, this is equal to a limit as n goes to infinity of the partial sum, which is k equals 1 through to n. So by definition of series, which is equal to the limit as n goes to infinity. So we know that sums commute. So, and this is from earlier in the course where we talked about segmentation. This is equal to AK plus BK through to n. Right, it's a property of, or rather that sums commute. And of course, limits distribute through the sum, so this is equal to a limit as n goes to infinity AK plus the limit as n goes to infinity and so this is a property of limits. And again, we arrive at the partial sums for the series AK and the series BK, and the limit of which is the whole series. So it's k equals 1 to infinity of AK plus k equals 1 to infinity of BK. And again, by definition of series. And these two properties come in handy because they allow us to break up a large complicated series into simple ones. So if I look at the series, something like 1 over k squared plus 1 over k cubed minus 6 plus 1 over sine k times k squared. Well, this can be broken down into three different series. 1 over k squared plus 1 over k cubed minus 6 sine k squared. Right, and these series are easier to deal with than the big series above, so easier to deal with. And very shortly, we'll see how we can actually compute the value of the first series. But first, let's look at another useful theorem. And this theorem is called, or it's about the tail of the series. So the tail of a series determines the convergence. So what do I mean by that? Determines convergence. So this means that the theorem is the series AK starting at k equals 1 to infinity converges if and only if the series starting at some n of AK converges just for all n. So recall, the series starting at k equals n, the definition of convergence is exactly the same, except that Sn is a sum from big N all the way up to little n. And intuitively this makes sense because if we take away or add the first few terms in a series, since we're only taking away or adding a finite number of elements, it should only have a finite effect on the series. Therefore, if the series goes off to infinity, taking away a finite amount won't make it converge, and vice versa. If it's finite, taking away or adding a finite amount won't make it diverge. Moreover, the whole series, the whole series starting at k equals 1 to infinity of AK is equal to a1 plus all the way up to an minus 1 plus the series if it starts at n. So let me give a quick proof of this fact. It's a proof. The sum k equals 1 to infinity of AK is equal to, by definition once more, limit as n goes to infinity of the partial sum k equals 1 to n of AK. And this is by definition of series. Now since we're taking the limit as n goes to infinity, we can only look at large N. So this we can split up as the limit as n goes to infinity of a1 plus a2 up to a big N minus 1 plus the sum is k equals 1 to n of ak. And this is for little n greater than big N. Sorry, this starts at k equals n. And again, we can use limit properties to bring out the first few terms. So this is equal to a1 plus a2 plus n minus 1 plus the limit as n goes to infinity of k equals n, little n. And once again, by definition, this is equal to the whole, so the limit is equal to, by definition, the series. So this is equal to k equals n, so starting at n, all the way up to infinity of ak, again, by definition. And of course, at this point, we can say that the right-hand side converges if and only if the left-hand side converges, which proves the theorem. Now let's look at a particular type of series called geometric series. So definition. A geometric series is a series of the form of the form to infinity of r to the k for some real number r. So examples of this would be for r equals 1/2. This is the series 1/2 to the k equals 1 to infinity, which is equal to 1/2 plus 1/4 plus 1/8, and so on. This is actually the series from our turtle example at the beginning of this lecture. Another example is just r equals 2. So the series is 2 to the k, which is equal to 2 plus 4 plus 8, and so on. So for geometric series, we can show that a geometric series converges if and only if r is less than 1. So let's express that as a theorem. So theorem, let r be a non-zero real number, then the series converges if the absolute value of r is less than 1. So if r is less than 1, the geometric series r to the k equals 1 to infinity converges, and it converges to 1 over 1 minus r. However, r greater than 1, or greater than or equal to 1, then the series diverges. Sorry, quick correction. This is k. This works only if the series starts at k equals 0. So to prove this theorem, we need to go back to the definition of the convergence of series. And the definition of series convergence looks at the partial sum. So again, we look at the partial sum. So consider partial sum Sn equal to, so again, we start at 0. So the first term is r to the 0 plus r to the 1 plus so on all the way up to r to the n. And note the r to the 0 is just equal to 1. Okay, now to compute a closed form for the partial sum, we're going to use a clever trick where we multiply both sides of this equation by r. So we have that r times Sn is equal to r to the 1 plus r to the 2 plus so on all the way up to r to the n minus, plus r to the n plus 1. And now we're going to subtract these two equations. So subtract these two equations. Subtract. So we get Sn minus r Sn is equal to r to the power of 0. All these terms here cancel, and Rn cancels, and we're just left with r to the n plus 1. And again, r to the 0 is just equal to 1, so this is 1 plus r to the n plus 1. Sorry, correction, this is 1 minus r to the n plus 1, because we're subtracting the second line from the first line. So from here we have, if we factor out the Sn on the left-hand side, we get that Sn times 1 minus r is equal to 1 minus r to the n plus 1. So that means Sn is equal to 1 minus r to the n plus 1 over 1 minus r. And this is true only for r not equal to 1, because if r equals to 1, then the denominator is 0, and this fraction is, it blows up. We'll come back to the r equals 1 case just shortly. So now to look at the convergence of the series, we need to consider the limit as n goes to infinity of Sn, which in this case is equal to the limit as n goes to infinity of 1 minus r to the n plus 1 over 1 minus r. And we know we can split up the limit between the numerator and the denominator, so this is equal to the limit as n goes to infinity of 1 minus r to the n plus 1 over the limit as n goes to infinity of 1 minus r. And this is a property of limits. And it's true if both the limits, the numerator and the denominator, have limits. Property of limits. Notice that the denominator here does not actually depend on n. So the bottom limit is just 1 minus r. So we're only left with the top limit in the numerator. So limit as n goes to infinity of 1 minus r to the n plus 1 over 1 minus r. And again, this is true for r not equal to 1. Or not equal to 1. And then if we, again, split up the limit in the top two terms, or in the terms in the numerator, this becomes 1 minus the limit as n goes to infinity of r to the n plus 1 over 1 minus r. Now we're going to consider the cases. So case 1 is when the absolute value of r is less than 1. So in that case, the limit as n goes to infinity of r to the n plus 1, we know this equals to 0. So that means the limit as n goes to infinity of Sn from the last slide is 1 minus the limit as n goes to infinity of r to the n plus 1 over 1 minus r, which is equal to simply 1 over 1 minus r. So therefore, the series r to the k from k equals 0 to infinity is equal to 1 over 1 minus r. And this is a case where for r less than 1, the absolute value of r being less than 1. Now case 2, we consider when r, the absolute value of r is strictly greater than 1. And in this case, the limit as n goes to infinity of r to the n plus 1 does not exist. Either goes out to infinity or oscillates between minus infinity and infinity depending on if r is positive or negative. Regardless, this means that the limit as n goes to infinity of Sn, which is again equal to 1 minus the limit as n goes to infinity of r to the n plus 1 over 1 minus r, this limit does not exist. So this implies that the series once again diverges because the limit of the partial sums diverges. Sorry, this should be k equals 1, and the series is... Okay, then case 3, we consider when r equals minus 1. In this case, the limit as n goes to infinity of r to the n plus 1, it also does not exist because if r equals minus 1, r to the n plus 1 will just oscillate between positive 1 and negative 1. So the overall limit will not exist. Similarly to the last case, this implies that the limit as n goes to infinity of Sn does not exist. And finally, the last case, r equals positive 1. This case is simple because this implies that the series r to the k from k equals 0 to infinity is equal to simply 1 to the k, which is just equal to 1 for all k. So this is 1 from k equals 0 to infinity, which is equal to 1 plus 1 plus 1, and so on. In this case, the partial sum Sn is equal to just the sum of n plus 1 ones, so this will be equal to n plus 1, which implies that the limit as n goes to infinity of Sn is equal to infinity. And once again, this implies that the series, the geometric series, does not converge, diverges. And this concludes the proof as we've covered all cases for r. So once again, the theorem is for a geometric series, if r is the magnitude of r is less than 1, then the series converges, and it converges to 1 over 1 minus r, and if the magnitude of r is greater than or equal to 1, the series diverges. So using this theorem, let's go back to our turtle example and see what the value should be. So our turtle, again the turtle example, the distance our turtle traveled was, distance traveled was equal to 1/2 plus 1/4 plus 1/8, and so on. Which is equal to, if you write it with sigma notation, is over k equals 1 to infinity of 1/2 to the k. Now by the theorem about geometric series, so by theorem on geometric series, we know that the series 1/2 to the k, starting at k equals 0 to infinity, is equal to, because 1/2, the magnitude of 1/2 is less than 1, this series is equal to 1 over 1 minus 1/2, which is of course equal to 2. And then using our theorem on the tails of series, we know that the sum from k equals 0 to infinity of 1/2 to the k is equal to the zeroth term, which is 1/2 to the 0, plus the distance our turtle traveled, which is the series 1/2 to the k. And of course, the geometric series starting at k equals 0 is equal to 2, and this is equal to, this 1/2 to the power 0 is equal to 1. So this means that this here is also equal to 1, because 1 plus 1 equals 2. And of course, this is the result we wanted, because we know our turtle has traveled a distance of 1, which is how we got this series, based on the fact that he must first travel halfway from 0 to 1, and then half of that, and then half of that, and so on. So our series, our definition of convergence of series is consistent with our intuition of the moving turtle. Okay, another example, let's consider the series minus 7 over 5 plus 7 over 25 minus 7 over 125 plus 7 over 625, and so on. So first we need to observe that this is in fact a geometric series, because if we factor out the 7, we get that 7, this is equal to 7 times minus 1/5 plus 1/25 minus 1 over 125 plus 1 over 625, and so on. And at each step, we multiply the previous term by minus 1/5. So this is equal to 7 times the series starting at k equals 1 to infinity of minus 1/5 to the k. And now this series starts at k equals 1. And if we instead want to start the series at k equals 0, we must add and subtract the k equals 0 term. So if you add this k equals 0 term to the series, so k equals 0 to infinity, and then we must take it away, so we must subtract 7 times minus 1/5 to the 0, which is of course just equal to 7. So again, by using the theorem we just covered, this is equal to 7 times 1 over 1 minus r, since in this case r is 1/5, minus 1/5, minus this 7 here. Right, and of course this is because minus 1/5, the absolute value of minus 5th is less than 1. And this simplifies to 7 times 5 over 6 minus 7, which is equal to 7 times 5/6 minus 1. So these geometric series are a very important example of a type of series. But we still need a way to find convergences and divergences of more series in general. And for that, we have something called convergence and divergence test. And we'll begin today by talking about divergence test. Now the divergence test, as it sounds, is a test to determine if a power series diverges. Next lecture we'll also talk about a few convergence tests, which are, as they sound, tests that determine if a power series converges. But today let's talk about the divergence test. So theorem. If a series AK starting at k equals 1 to infinity converges, then it is necessarily true that the limit of the sequence AK must equal 0. Intuitively, this makes sense because if the term ak is not going to 0, that means that the power series is an infinite sum of numbers which are, for lack of a better term, not infinitely small, which means the sum will be infinity, or it'll oscillate or do something weird. Again, this will make more sense as when we prove this theorem, but the reason this is called a divergence test is not for this statement, but actually it's contrapositive. So the contrapositive to this statement, or this theorem, is that if the limit of the sequence ak from k goes to infinity is not equal to 0, then the series must diverge. The series diverges. Right? So if a series converging implies that the limit of the sequence is equal to 0, then if the limit of the sequence ak is not equal to 0, the series must diverge. And this is the reason it's called a divergence test. So before I do some examples of how to use the divergence test, let's first prove the theorem. We can prove the first statement because, again, the contrapositive is logically equivalent to the original theorem. So proof. Suppose the series to infinity, suppose the series converges, and it converges to some value, let's say L. So we know that the limit of the partial sums is equal to L. Now the partial sum Sn is equal to A1 plus A2, again all the way up to An, and Sn plus 1 is equal to A1 plus A2, all the way up to An plus An plus 1. Once again, we're going to subtract these two equations. I'll subtract the top line from the bottom line, so this gives us that Sn plus 1 minus Sn is equal to, and all these terms here cancel, and we're left with just An plus 1. Once again, I'm subtracting the top from the bottom. Now the limit as n goes to infinity of An is equal to the limit as n goes to infinity of An plus 1, because again, n going to infinity also implies that n plus 1 goes to infinity, so you could do a simple change of variables. This is equal to the limit from the above line of n goes to infinity of Sn plus 1 minus Sn, which if, again, we distribute the limits, this becomes the limit plus, and I'm going to run out of space here, Sn, and this is equal to L minus L, because both these limits are L, which is equal to 0. So this shows that the limit as n goes to infinity of An is equal to 0. So to do a few examples, we can actually use the divergence test to show that the geometric series of k equals 0 to infinity of r to the k diverges for r greater than 1. And this is because the limit as k goes to infinity of r to the k is equal to, well, this limit goes to infinity if r is greater than 1. And of course, infinity is not equal to 0. Therefore, by the divergence test, the series diverges. converges. Now let's do another example. Let's consider the series k over k plus 1 to the k. And the question is, does this converge or diverge? Diverge. Again, we want to use the divergence test here. So we look at the limit of the individual terms in the series. So let's consider the limit as k goes to infinity of k over k plus 1 to the power of k. Now this limit, I can take the reciprocal of it. So this is equal to 1 over the limit as k goes to infinity of the reciprocal of the fraction, so it's k plus 1 over k to the power of k. And this is equal to 1 over limit as k goes to infinity of 1 plus 1 over k to the power of k. And this limit here should look familiar. If you recall from A31, this is equal to e. So this whole limit is equal to 1 over e. And of course 1 over e is not equal to 0. Therefore, by divergence test, the series k equals 1 to infinity of k over k plus 1 to the k diverges. So in general, if you're given a series and you want to figure out if it converges or diverges, a good first step is to try to see if you can use the divergence test. That is to say, look at the limit of the individual terms. Is it equal to 0? If it's not equal to 0, well, you know by the divergence test that the series diverges. If it is equal to 0, well then you don't know if it converges or diverges. You have to use some of the convergence tests, which we will cover next week. But let's finish off with one last example. So let's consider the power series 1 over k equals 1 to infinity. And does this converge or diverge? So again, we want to use the divergence test as a starter. Limit as k goes to infinity of the individual terms 1 over k. Well, this is equal to 0. So what does the divergence test tell us? Well, it doesn't tell us anything. So the divergence test is not useful here. Test is not useful. Note that this does not imply that the series converges, because the converse of the divergence test is not true. Just because the terms in the series have a limit that go to 0, it does not imply that the power series converges. And this is one good example, because this power series does in fact diverge. But in fact, the power series 1 over k diverges. And we'll see in the next lecture, using some convergence test, why this is the case. But right now, let me do a separate argument. If I expand out this power series, it looks something like this. So 1 plus 1/2 plus 1/3 plus 1/4. I'm going to write out the first few terms. 1/7 and so on. And notice that the first term, this whole thing is greater than. This is greater than 1 plus 1/2. I'm not changing the first two terms, but the third term, I know that 1/4 is smaller than 1/3. So this whole the line on top is smaller than if I had 1/4 instead of 1/3, plus 1/4. So this is the same 1/4 as here. These correspond. And again, I can 1/5 is less than 1/8, or sorry, 1/5 is greater than 1/8. So is 1/6. So is 1/7, and then of course 1/8 is just 1/8. And you can repeat this argument over and over again. But then we get that this is equal to 1 plus 1/2 plus, well, this is equal to 1/2 plus these 4 terms are equal to 1/2 plus, and so on. And this is equal to infinity because we're adding up 1/2 an infinite number of times, so that means it'll go to infinity. And since the series is greater than infinity, that implies that the series must diverge because it's greater than infinity. Diverge. And we're going to stop there today. Next lecture we will cover convergence theorems and more on series. Again, if you have any questions about this lecture, please post on Piazza. I'll be following Piazza regularly and answering any questions as they come up. Thank you.